All right. Well, I don't know. Do you guys have questions, comments, anything before we get started? Yeah.
When are the midterm grades going to be?
When will the midterm grades be? Okay. I've talked to the graders there. I think they said they're going to finish by the end of the week. That's the hope. So, yeah, I don't know. Okay, but yeah, and I know in 102C, it's like both of those graders are super behind, but they're both working on their thesis, so I'm sympathetic to that. But this one, I think they're just working. So okay. Anything else? All right. Well, today we'll take a look at kind of this idea of feature engineering. Okay, so the previous couple lectures were about cross-validation, which is very important as far as checking to see if our models are correct, because again, with scikit-learn, we are not taking the traditional statistics approach where you have p-values and things like that. You just kind of fit a model and see how well it does at predicting things. And if it does good, then it's a good model, okay? And, you know, of course, then you need to take your training data and split it into like a training and a validation set. And, you know, we do cross-validation to kind of just make sure that, you know, whatever model we fit can predict the, you know, values it hasn't seen. All right, with feature engineering, we are often creating new variables. So your input matrix X might only have a certain number of variables, and then from there, maybe you need to derive additional variables or something like that, okay? And so that's kind of the idea of feature engineering. So in scikit-learn, we call our predictor variables, the explanatory variables, features of the data, okay? And scikit-learn requires everything to be a numeric matrix going in, okay? So if you've got categorical data, you've got to like turn them into dummy variables, or you do something to turn everything into a numeric matrix, and then you've got kind of your predicted target, which will be just a single, you know, a one-dimensional array, and so that's how we'll go. So so first we'll take a look at just categorical variables, and you know, there's several ways to do this. Pandas actually has something called get dummies, but here I'm going to use scikit-learn's one-hot encoder, okay? And by using scikit-learn's things, you can put them later on into something called a pipeline, okay, a processing pipeline. And so with scikit-learn, we have something called the one-hot encoder. And so what this will do is, you know, if you've got a categorical variable, you might be tempted to turn this into like R-style factors, where each level gets a integer value, like red gets the integer value 1, and blue gets the integer value 2, and yellow gets the integer value 3. But this is actually not good, because scikit-learn is going to see that column 1, 2, and 3, and it's going to treat the rows with yellow as having 3 times more, you know, whatever, than the rows with red. So instead, you're going to have, you know, a column for red with 1s and 0s, with 1 if it is red, and 0 for everything else. And then you'll have, so one-hot encoding does this, all right? So you're gonna have a column for red, and then a column for yellow, and a column for blue, or a column for blue and yellow, if it's yellow and everything. All right, so anyway, so we'll do that. Okay, and so I'm going to import one hot encoder from pre-processing. Right? I've got, I don't know, I just took the Titanic training data from Kaggle, okay, and this is what it looks like. And so I'm going to just do this to two of the variables, sex, which is encoded as male or female, and class, which is 1, 2, or 3. Okay, so this is right now passenger class is a numeric variable, but we don't want to treat it like a numeric variable. Okay, and so we can one hot encode passenger class, even though it's numeric already. We can do one hot encoding. With sex, you know, I'm going to do one hot encoding. Whenever you do this, one of the columns ends up being redundant, okay? Because if you have a column for male and you have a column for female, and the male is 1 and the female is 0, or the male is 0 and the female is 1, like you can get rid of one of those columns and figure out what the other one is, okay? Same with, like if you have 3 categories, A, B, and C, and you do one hot encoding and you get 3 things, you know, if it's A, it's going to be 1, 0, 0. If it's B, it's going to be 0, 1, 0. And if it's C, it's going to be 0, 0, 1. And you can just get rid of one of those columns and you can figure it out, right? So if you just keep columns A and B, you'll have 1, 0, 0, 1, or 0, 0. And if you see the 0, 0, you know it's going to be column category C. So, I mean, there is an option to, I think in the one hot encoder to do that. The default thing is sparse is true, but you know, when you do that, you can't actually see what it does. So if you just do one hot encoder and you just use the default settings, which is fine, you can, you know, then fit it, you're going to get something like this. You're going to get an 891 by 2 sparse matrix, which maybe we don't actually, well, as far as being able to see it, you have to say sparse is false, and then it actually creates the matrix with the values. Okay, and so we can see it goes male, female, 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 male, and I guess we can just do the first 4, and we can see you know, that indeed it encodes it, okay? So this column is for female and this column is for male. Okay, so the way it works is you call, you say I'm gonna you initialize your one hot encoder, and I'm just calling it ENC for encoder. And then there's a few things, but you can just fit it, but then there's fit transform, and so here I'm doing fit transform, and I'm asking it to do it to the column sex, okay? And so here, you know, it's expecting kind of this matrix thing, so we feed it the column sex, and then it encodes it appropriately. Then you can also ask, you know, what are the corresponding categories, and it tells you the first column is female and the second column is male, okay? And so you can then kind of pipe this all together, or not pipe it all together, but throw it all together into a data frame. And so here I'm saying make a data frame out of this thing, fit transform on Titanic, and it gives us kind of that 891 by 2 matrix, and then we label them with the column names from encoding categories. Okay, and we have it right here. And this allows us to do that.
I'm just curious, what's the underscore? Is that something about like a member variable? Sometimes we have an underscore when we access.
Yeah. I don't know. I want to say it's generally it's kind of like underlying values. We usually throw in this I mean, it's just part of the specification. Let me see. So if I do one hot encoder, so it gives you back, so these are the parameters, and then as the attributes that it returns, they just have the underscore in the name, okay? And then, and it used to return these things also, but these have all been deprecated, so they're removed from the feature. So sklearn is constantly undergoing changes and stuff, and so you just have to be prepared that like your code that you write today or 6 months ago, might not work in 6 months or something, or you'll get like. You see, when they deprecate something, they'll usually leave it in there for like a couple, I don't know, future updates, but it'll keep flashing these like warnings, and then and that's a key to say like, oh, I gotta change my code, because later on you won't get the warning, it'll just crash, and you won't know what happened. Okay, or I mean, it'll just say like this thing doesn't exist. So yeah, once you do it though, the methods are all here. The methods all have parentheses to kind of indicate that they're functions, and then yeah, some of these things, yeah, the attributes have these underscores, but I don't know. Okay, yes.
Can you just go over again when we use fit and fit transform, like the difference between the two?
So okay, yeah, let's see. You're testing me on stuff. All right, so I'm gonna just initialize the one hot encoder, and when you do one hot encoder on fit, and you call fit, and you just do it to the variable that you're interested in, you just get back this one hot encoder thing. You can then take this and throw it into something, okay? So it just fits the encoder. Yeah, I know. It's just weird. All right. It happened in my other class, like the exact same thing. Just some random person walks in, grabs something, walks out. Yeah, I know, right? It's all right.
Oh my God.
Okay. So anyway, you just fit it, and what it does is it returns itself, which returns basically an encoder, which I don't know. It's just a little bit weird, right? So, so here, if I just ask for this, let me see. Okay, so let me just restart the output. Did that work? Okay, kernel ready. Okay, so we'll do that. We'll import the encoder. We'll read in the data. So a lot of things in sklearn, you just kind of initialize these tools, and it will just say we have this thing, okay? And then when you just run fit, it just keeps it. It just returns itself after it's kind of updated its internal values. Okay, you can't really tell if at some point you wanted to then say enc transform. Okay, then it will return the values. Okay, if I initialize this without fitting, it's gonna complain. Okay, so you have to initialize it, you fit it, and then you can transform it and get this out. Okay, fit transform does both of these things in one step. Right? There are other things, I guess. So why would you want fit? Is like there's other things you can do with the one hot encoder. I don't know. There's other I don't know, other things you can do. I don't know them off the top of my head here. But as far as pre-processing goes, you can take kind of the encoder and do other stuff with it. You know, most of the time you're going to fit and then you're going to transform the input. And so, you know, fit transform is kind of a natural single step to do it. But you can fit it, do other stuff before you finally kind of ask for the transformed output, or you can, you know, use whatever. Okay, and then, yeah, we fit it all together in the data frame. Here I'm going to do the same thing, except with passenger class, which is currently an integer. And so what the one-hot encoder does is it will search through that column, look for unique values, and basically turn each of those into categories. Okay, and here I just kind of specify categories as auto, and then it says, oh, okay, I recognize 3 different categories, you know, category first class, second class, and third class, and it transforms them accordingly. So we have, you know, third class passenger, first class passenger, third class passenger, and we see, you know, we have a 1 for the third column, a 1 for the first column, and a 1 for the third column. And then the categories are 1, 2, and 3. And so if we do that, we get, I mean, we can kind of feed this in. Here, what was I doing here? This was one-hot encoding for multiple columns at the same time. If you just throw the entire data set into one-hot encoder, it's going to try to one-hot encode all the variables, okay, which could be like disastrous, not disastrous, but it's going to, like, you might have something that's numeric and it's going to try to one-hot encode it. And it's going to get messy. The one issue though is that it doesn't know what to do with missing values. Okay, it doesn't know how to do a one-hot encoding for missing values. So, you know, there have been arguments online about how it should do it, but nobody can agree. You know, so anyway, if you do stuff, you might have to do drop NAs to get rid of it. Here we've got these 2 categorical things, and then you can kind of one-hot encode them. And because I have three categories for class and 2 categories for sex, the result is going to be end up having 5 columns. And we can kind of look at results dot. Now this is not going to work. Okay, we kind of just the first 5 columns, so we can see the, you know, third class and male, first class female, third class female, first class female, things like that. Okay, I mean, it requires you to kind of do this. Unfortunately, if you wanted to like make a data frame out of this, we have a list of lists. Okay, so we have a list with the list 1, 2, or it's a list of arrays. Okay, we have 1, 2, 3, and then female, male, and then so you have to do a list comprehension to kind of flatten out the list. Okay, and this says for X in encoding categories. So the first part is like for each array. Maybe I'll call this for array in encoding categories, and then for value in array. Maybe this will make more sense. Then return the value. Okay. So you're doing it for each array in the list of lists, or list of arrays, and then you do this. It's kind of like it's a loop within a loop, and return the values. So anyway, you do that, then you can kind of get your one-hot encoded categorical features. All right. Other things that we might do is try to develop text features, okay? And so here we have some text, and I'm using just the example from Jake Vanderplas Python Data Science Handbook. And so we have these three strings: the problem of evil, evil queen, horizon problem. Okay? And we're going to, from sklearn feature extraction.text, we're going to look up the count vectorizer. Maybe I should include links to the help for each of these things. Okay, so we pull the count vectorizer, and we initialize the count vectorizer, and then we do fit transform, okay? Just like so many of these other things we're doing. Well, a nice thing about sklearn is that things that do similar stuff are all kind of used in a similar way. So, you know, you can call fit transform. You can call fit, you can call transform separately. And in one step, we'll do fit transform, okay? And so here it creates a sparse matrix. You can then call x.toArray, and it returns this. If we call this thing get the feature names, it's going to tell you what word corresponds to each kind of column, and we have this, okay? And so the first one was the problem of evil, okay? And so it gives me a 1 for problem, 1 for of, and 1 for evil. And then we have evil queen, and then we've got horizon problem. So this is what we have here. Okay, and so it kind of does this. We had a total of 5 unique words and things like this, okay? The raw word count, however, can lead to certain problems, okay? And so there's something called the term frequency inverse document frequency matrix, okay? And so there's this thing, the term frequency inverse document frequency vectorizer, okay? Everything, our favorite. And what this does is it kind of, I should put this in a markdown thing actually. So let me just kind of show this to you, is that it weighs these according to how often the word appears and how many words appeared in the document, okay? So values are weighted according to how many times the word appears and how many words are in the document, okay? So, so for example, the word horizon appears only one time in the entire kind of corpus of documents here, okay? And in all of these things, the word horizon appeared only once, and so it gets a high weight because as far as the horizon column goes, there's only, the thing shows up only one time. And so, so it gets a weight of, you know, I don't know, 0.795691. I forget. Term documents inverse frequency matrix. Let's see. It is calculated as the product of the term frequency multiplied by the inverse document frequency, okay? And so this is the, kind of the formula it uses. And so, but basically the idea is if a document has lots of words, then those words will kind of get weighted less. If a word appears only in one document, then it's going to have a high weight for that one document, right? So for example, the word of, so let me just kind of point out a few things, okay? The word of only appears in the first document, okay? But the first document has 3 words. So its weight is 0.68, okay? Meanwhile, the word horizon appears only in the third document, okay? And the third document only has 2 words in it. So each word is weighted more, and we get horizon is weighted 0.796, okay? And as far as the word evil goes, it appears twice, okay? It appears in the first and second document. Okay, so each appearance is, weighted a little bit less, but it's weighted more in the second document. Weighted a bit less, okay? It's worth more in the second document, which only has 2 words, and worth less in the first document, which has 3 words, okay? And so it kind of gives like a loose association between, how frequently does this word appear, and how strongly is it associated with a certain document and things like that, okay? So this is the term frequency, inverse document frequency matrix, okay? And this is kind of a frequently used thing. Maybe I'll link to the Wikipedia article as well. So that's that's that, and this is the other part, okay? So, but yeah, you can just go straight with word counts as well, okay? Word counts is fine, but then, the problem with word counts is that if there's one document that's like 1,000,000 words long and another document that's only 100 words long, the 1,000,000 document word is going to have way more word counts, okay? And so like the 100-word document may be entirely about I don't know, cars or something, and it's just straight about whatever cars, and then the 1,000,000-word document touches on like 50 different topics and uses the word cars like 100 times or something like that, okay? So its word count's going to be, for the word cars, is going to be much higher. But by having kind of this term frequency and inverse document frequency together, it'll weigh them accordingly. Okay. So another thing that we might have to do is fill in missing data, okay? So you might have some kind of matrix or an array with missing data, and so we have some missing values. And so we have something called an imputer, All right, we can look up simple imputer, and there's lots of, how many you got? I don't know, all of these things. And the default strategy for imputing is to kind of plug in the mean. This may or may not be a good strategy, okay? So, you know, when you have missing values, so I should say, imputing the mean is not always the best strategy, so warning. Filling in the mean is not always the best strategy. Okay, perhaps you need to use the EM algorithm or something. Okay, but the simple imputer is great for filling in with simple rules like the mean. All right, so sometimes filling in with the mean is an okay strategy. All right, and in that case, you can just do initialize the simple imputer, and then you fit transform on your matrix X. Okay, and so here we say strategy is equal to mean, and it's going to fill in the mean. And you can do other things like the median most frequent, a constant, okay, and then you fill in the thing, okay. So if you want, you can do strategy is we'll do constant, and we'll do fill value equals 0 or something like that, okay? And then it'll fill in zeros for your missing values. So, or, you know, negative 99. It's allowed, okay? Okay, and then you know, once you have the you filled in the missing values, then you can just do something like linear regression with it or something like that. Okay. I think I showed this on an earlier one, but there's you can derive polynomial features. Okay, and so for example, here's x 1 2 3 4 5, and you can call polynomial features. Okay. Polynomial features, you initialize that, and then you do fit transform. And here, degree 3, it's going to take our x, okay, so here I have to reshape it from a one-dimensional array into a two-dimensional, just a column array. And so then it goes, you know, 1 2 3 4 5, then we have squared values, you know, 1 4 9 16 25, and then cube values, okay. If we did include bias true, then it includes a column for the ones as well. So I don't know, maybe I actually want that. All right, so you can do that. Include bias will include basically 0 power column. So you take each value and raise it to the 0 power, and you'll get that. Okay, and then here, you know, now that we have our model x2, we can specify, you know, linear regression, and then fit our feature matrix x to y, make a plot, and then fit the data or something like that. Is that okay? I don't know if I'm doing this too quickly. All right, so these are just kind of different things that we can do to kind of create or derive new features. And then sometimes, depending on what you're doing, you might need to do the same task for like different sets of data, okay? And it can become kind of like annoying and tedious if you have to say, all right, first we're going to fill in the missing values, then we're going to do a polynomial transform, and then we're going to fit linear regression, okay? And then we're going to do this for this data set, and do it for this data set, and do it for this data set. And so you can create something called a pipeline, which is basically, it's almost like a, I don't know, a list of instructions. And it says, you know, first do this, and then do this, okay? And so here we call sklearn make pipeline, and then and the pipeline is basically do simple imputer on your x's, then do polynomial features of degree 2, and then fit linear regression, okay? So it kind of just says, you know, follow these steps. And so, so here we have x and y, and then we do fit x and y, okay? And so what it will do is it'll do simple imputer, and then it'll fit the x, and then it'll do polynomial features, and it'll fit the x, and then it'll do linear regression, and it'll fit the kind of the x and the y there, right? And so in this case, you know, we save some, I guess, clock cycles without having to do fit transform each time. We can just kind of fit the x, and scikit-learn kind of keeps the internal structure, and it will do that. And so here, it fits it, and then it kind of creates our predicted values and things like that. And here, I guess it just you know, we're creating the model here. But if you ask for the model, it's going to say it's this pipeline where the steps are the simple imputer, the polynomial features, and linear regression. Okay, but you know, that's what you have. And so you can then take a different data set and do something like it as well. Let me see. Maybe I can just do. So here's another data set, and I'm going to go ahead and I'll just throw in a nan here. Okay, so it's going to fill in the mean of 1, 2, 3, and 5, which is probably, you know, is the wrong value. Okay, but we can still. X is going to be x dot reshape 5, 1, and then we'll do model dot fit x, y. Oops. And then we'll do model dot predict on my x. All right, and it gives me these values, which are not great. Well, they're okay. They're okay. Let's just see. Let's plot. Now, PLT. PLT will do x and y. I'm sorry, PLT dot plot x and y. And then PLT dot plot x and predict x. Oh, model dot predict x. Okay, so this is what it ends up. Oh, we get because I've got missing values, it doesn't like it. We'll just compare how the y's versus the model.predict x looks. What is that? Probably scatter is better. Okay, so not the best, but you know, 4 versus 4, 2 versus that. 1 is getting predicted to 2, and 3 gets predicted to 1, and 7 gets predicted to 7. So that's, I mean, that's good, and it's because my missing value is at the 4. If my missing value is at the 3, which lines up perfectly with the missing, then our predictions are good. So yeah. Anyway, you know, we're trying here. We're imputing missing values by using the mean, and so you know where the missing value is matters. So here, you know, you're trying to fit something that maybe it's not the best, but anyway. So the pipeline can kind of simplify your work, especially if you're doing kind of the same repeated kind of data cleanup type of stuff, all right? And so if you're able to kind of tell all of your steps using sklearn without kind of like manually saying like search for this term and replace it with this or something like that, but if you can turn your data pre-processing and cleanup steps using sklearn's tools, you can set up a pipeline to kind of streamline your work in a very nice way. You know, sometimes it's unavoidable and you have to say like find this and replace the spaces with this, but other times there's a lot. And so there's a lot of, you can look up sklearn pre-processing, and there's a bunch of stuff, right? So you can scale your data. This is the standardization, mean removal, variance scaling, nonlinear transformation, normalization, encoding, discretizing, so that so these are all sorts of different things. So discretizing so encoding takes a categorical variable and turns them into kind of numeric things, and discretizing will take a numeric thing and kind of bin them up into like categories pretty much, all right? So you can say like, rather than taking people's heights, numeric heights, you can say like, you know, bottom 20%, next 20%, middle 20%, you know, top 20%, things like that. So that's what discretizing will do. Imputation of missing values, polynomial features. So there's lots of stuff that can be done as far as pre-processing your data, okay? And then another thing that is great that we haven't covered, but you know, you can do like one-hot encoding for a huge thing, and then after that, you can then apply something like PCA, which principal components analysis, which will reduce the number of dimensions you're dealing with. There's lots of stuff that can be done. So this is just, I think this is kind of going to be like the most commonly used things as far as feature generation goes. But of course, you can always read the documentation and find more tools to use. But I think this is a good selection of some pre-processing tools. Okay. How are your projects coming along as far as, I don't know, at least the exploratory data analysis? You should be able to get a good amount of work done there, you know, if you spent time on it. But anyway, again, if you have questions about your set, please come to office hours. Not very many people have come by asking for help or advice on their projects, so I'm gonna cross my fingers and hope that means your projects are going well, but realistically it might just mean maybe we're not making as much progress as we should. But anyway, yeah, so don't hesitate to stop by. I'm happy to take a look at your data and stuff. Okay, we'll see you guys on Friday.